In this segment, we'll finish the transactions discussion by looking at serializable isolation, phantom reads, and default isolation levels. Now, if you're not into hand locking rows, you can get any DBMS, even MySQL, to do it automatically by setting the isolation to the most strict level, serializable. The standard for serializable isolation is that the behavior of the two transactions must be exactly as if one transaction had run and committed entirely before the other transaction was started, as if they were run serially, thus the name. The transactions don't literally have to run serially. They can run simultaneously as long as the serialized illusion is maintained. But any behavior like the overwritten $100 addition that has bedeviled most of our prior attempts is automatically precluded by serializable isolation. So let's retry the select and update version of our example under serializable isolation, which will induce MySQL to use row locks automatically. And we start with transaction or session 1 using serializable, as you can see, isolation, and getting a select on row number 3. Now, the row locking is a bit more complex than in the repeatable read examples, in that there are two levels of locking. Under serializable isolation, MySQL places a shared lock on the row read by session 1 in this first select. This marks the row as having been read by session 1 and in effect says other transactions can read this but may not modify it till session 1's transaction is done. Modification might cause an uncommitted or non-repeatable read in session 1. So session 2 gets a similar shared lock when it does its select. So far, the two locks are compatible, and either session can keep reading the data. But when session 2 reaches its update statement, it needs an exclusive lock, which in effect says, this row is all mine, and no one else can count on its prior value since I'm about to change that. Session 1's shared lock precludes session 2's exclusive lock, so session 2 must stop and wait for session 1 to commit and release its lock. Now, if all session 1 was planning to do was use the row 3 data without modifying it, then session 2 would just wait for session 1 to be done. But session 1 also wants to modify the row, and when session 1 reaches its update statement, it also seeks an exclusive lock on the row. So question 1, what's about to happen and why? We saw a similar situation in the prior segment. The answer is a deadlock will result. Both sessions seek an exclusive lock on a row on which both already hold a shared lock, precluding either from getting an exclusive lock. And as you can see, the result is as before. MySQL forces one session to roll back and restart, leaving the other free to proceed and to go first. And just to complete the process, let's do session 1's restart to show that the whole thing does work. Session 1 now sees the 1250 that was just written by session 2, and it updates that to add $50, and the result is both updates succeed. Now, serialization or serializable isolation also prevents a subtle problem that can show up in repeatable read isolation, and this is called a phantom read. A phantom read occurs when one transaction selects a set of rows, for instance, select star from account where balance is less than 300. Do that in session 1 there. And another transaction adds a new row that would have been returned by the first transaction's select. So in session 2 here, we'll add a Taylor row with a 0 balance. Now, if this addition is committed, and if the first session repeats its select, there would be another row returned, one that was missing earlier, since Taylor qualifies as a balance less than 300. This would be a phantom read. It differs from a non-repeatable read in that it's not a matter of a previously selected row changing its value by surprise. Instead, a phantom read presents an entirely new row that was not present before. Serializable isolation prevents phantom reads, as the example shows. The phantom row generating addition here in session 2 is blocked until session 1 completes. So session 1 can be sure that its select repeats the same value with no added phantom rows, and then once it commits, then session 2 can proceed, and we see the new row. It's worth noting that MySQL's system of giving transactions a copy of the data to work on prevents phantom reads even in lesser levels of isolation, since newly added rows simply remain invisible to the transaction until it commits. But this is unusual. In a DBMS that does isolation by locking rows, stopping phantom reads is done only at serializable isolation, because it's especially difficult to do by locking. The DBMS must lock an entire range of possible rows, for instance all those with balance less than 300, preventing session 2's addition of the new Taylor row until session 1 has committed or rolled back its transaction. Now, phantom reads aren't a problem in most cases, so repeatable read isolation is often enough unless you really care about phantom reads or if, as in MySQL, you want row locking to be done automatically. Now, we've been setting isolation levels by hand before starting each transaction, but you don't have to do this. Each DBMS sets a default isolation level, which you get if you don't specify otherwise. For MySQL, that default is repeatable read. For some databases, the default is read committed. Those two middle ground choices are usually the best. Serializable isolation is more expensive, and read uncommitted is sloppy and not that much cheaper than read committed. You can also, as I just illustrated here, set the isolation level for all transactions in a session without having to do so at the start of each one by adding the keyword session before transaction. So set session transaction isolation level serializable would set all the transactions in the current session to serializable until you specify otherwise. So that ends our transaction discussion. Here's a summary of the main points. First, transactions arrange for groups of SQL actions to be taken as a whole, atomically. Second, transactions ensure atomicity, consistency, isolation, and durability, the ACID acronym. 3. There are 4 standard levels of transaction isolation defined generally, but implemented somewhat idiosyncratically by different RDBMSs. 4. Read uncommitted isolation is fast but sloppy, permitting even dirty reads of data that is uncommitted and may be rolled back. Read committed is a little more careful, preventing dirty reads but still allowing surprise non-repeatable reads where commits by other transactions suddenly change the data. Repeatable read ensures that any read done during the transaction will repeatedly provide the same result until the transaction is done, even if other transactions are changing the data. Repeatable read can be done by providing a copy of the old data to a transaction, ensuring it always sees the old value, or by locking, which prevents a transaction from seeing a value until any pending update is done, thus ensuring it sees the new value. MySQL uses copying. Copying results in fewer blocked transactions, but also invites overwritten updates. And you can prevent that by explicit row locking via select for update. Under serializable isolation, the strictest level, overwritten updates are prevented automatically, and even MySQL will use row locking to do this. Row locking can cause deadlocks, which DBMSs automatically detect and solve by picking one transaction on which to force a rollback. You should try to avoid deadlocks by locking rows in the same order in each transaction, but always be ready to have your transaction forced to roll back if a deadlock results. Phantom reads, by which a new row suddenly appears in a transaction, are prevented in serializable mode, and under MySQL in repeatable read mode too. And then finally, DBMSs usually define a default isolation, either read committed or repeatable read.